Good morning, class. So we are going to start something a little bit different. I'm going to look over Friday's answers before getting into Monday's work. So Friday we were still going over creating rules for tables using one step. So I just wanted to actually focus on the last one. A couple of you didn't do the rule. I made a note of it. The last one was a trick one, so I did want to go over it. So we had 5 and we went to -5. We had 6 and went to -6, 7 to -7, and 8 to -8. So my most common answer is actually 0. You added 0 to it. That couldn't be the case though, because we went from 5 to a -5. So that actually is a difference of 10. So we adding 5 and -5 are not the same thing. If you remember the number line, they're actually on the opposite sides. So that was incorrect. What was happening is we were multiplying by the negative. So if you go back to your integer rules, remember that a positive, so positive 5 times a negative would equal a negative. That was kind of the clue that would tell you that it was a -1 that was multiplying by. So 5 times -1 equals -5. 6 times -1 equals -6. 7 times -1 equals -7, and 8 times -1 equals -8. The reason I'm going over this is very, very commonly used. Looking at how I set up the rule, I have f of x equals x times -1, which can simplify to -1 times x, remembering that the multiplication is assumed when the coefficient and the variable are next to each other. And also, remembering Daniel's rule, we can take out the negative, the 1, and leave the negative, so it's just negative x. So I took out the 1, just left the negative. I also wanted to go over the riddle question, thanks to Jose. What can you break even if you never pick it up or touch it? And his answer was a promise. All right, so now we're going to get into Monday's work. And if you notice, I highlighted we're working with 2 operations. This is the step up from what we were doing yesterday. You guys did a great job finding patterns and making linear equations, so now we're going to get into it. An operation is addition, subtraction, multiplication, or division. So I'm going to tell you that it's going to be mostly addition or subtraction and multiplication. A function equation is an equation where every input has only one output. That's what we've been working with. We're going to continue working with the linear equation, the line equation, which is an equation which creates a line due to the constant rate of change, which another way to say is the m stays the same. So basically, it's a way to say that this equation is the rule for the entire table, which is what you guys are picking up based on the patterns we're determining. So our steps for determining a rule for a linear function is examine the input and the output and ask yourself, how did the output turn into the input? And I cannot recommend enough to try all the operations. Again, we're really just focusing at this time on addition, subtraction, and multiplication. Once you have an idea, you have to test each pair. This is something I noticed when I was reading your work from Friday, but sometimes we didn't have all the pairs tested. So you have to make sure it works for the entire table, because that's why it's a rule for the entire table. If it works for each pairing, then you have to write it in terms of x and f of x, remembering that f of x is the same thing as y. So it will be f of x equals mx plus b, and I wrote this little note here, that the plus or minus that we do in our rule is going to be the b, and anything we multiply is going to be the m. So you can always come back to f of x equals mx plus b, because that is our guiding equation when we're working with linear equations. Now let's get into number 1. So we're going to start off soft. I have 0 to 1, 2 to 5, 4 to 9, and 6 to 13. Now I'm telling you guys right away that this is 2 operations. We can easily prove it too. There is nothing that I can do to a 0 that will get to 1 in one operation. That will be the same for 2 and 5. Once you see that, you know that you're thinking about 2 operations. Another thing to think about is we're working with zeros. The minute you work with zeros, that is a good clue that they're multiplying something and then adding something. So whatever you multiply to a 0, that's actually going to become 0. So this is just going to tell us what we added. So 0 times anything will equal 0, and then plus 1 would equal 1. So we know it's going to be a plus 1. Now we have to figure out what we're multiplying by. So let's look at the 2, 5 pairing. So we have a 2 and it turned into 5. So we know that we added the 1 to get to the 5. So we can kind of think backwards. So if we had 5 minus 1, that would equal 4. So what would 2 have to multiply to equal 4? Well, 2 would have to multiply by 2. equal 4, and then plus 1. So now let's look at what we just created. We have 2 times 2, which is equal 4. And then we have plus 1, which would equal 5. Now, if it works here, we have to make sure it works everywhere. So let's go back to the 0 and the 1. So we have 0 times 2, which would equal 0, plus 1 would equal 1. So it works there. Now I have to try one more time, or 2 more times, I like. So 4 times 2 equals 8, plus 1 equals 9. So far, so good. We always want to check the entire table, though. So 6 times 2 equals 12, plus 1 equals 13. That means we found the rule. Now we have to write the rule in terms of f of x. So we're going to write f of x. We're going to use our parentheses correctly. And I said the m is whatever we multiply. So looking at where I asked you to show the work for our rule making, we notice that we multiply by 2. So that means it's going to be a 2 times the x. And then the b is whatever we add or subtract. So we plus 1. That's our final answer. Question 2, I did throw you a negative, but I threw you a gentle negative and I gave you a 0. And I cannot recommend enough really thinking about how we use the zeros. So we have -1 to -4. We have 0 to -1, 5 to 14, and 12 to 35. I kind of brought it all over the place for this one because I think it might be a little bit easier. Starting with the 0, it already gave us information. Anything times a 0 is going to equal a 0. However, it has a -1 as its answer. So that means whatever we did multiplication, we minus a 1 at the end. So that gives us information. Now the opposite of -1 is +1. So let's look at 5 to 14. If I were to add 1 to 14, that would equal 15. 5 times 3 equals 15. And then we subtract the 1, and that would equal 14. Now we have to make sure that it works for all of them. So we have 0 times 3 equals 0. Kind of the gift of the zeros, they tell us a lot of information. 0 minus 1 equals -1. Now let's make sure it works for the first one. We have -1 times 3, which would equal -3. We subtract the 1. -3 minus 1 equals -4. 12 times 3, so last one, times 3 equals 36. Practice these before I do them with you guys. 36 minus the one we identified equals 35. So it worked out for each one. Again, we look at the 0, it gave us the most information, and after that we can kind of guess around. Another way to do it that I really recommend, if this works for you as well, is you kind of look at a pairing that you know the multiplication tables of really well. So for example, I know 5 times table really well. So I would look at that and I would think, well, how can I get 5 as close as possible to 14? And that's when I go back. Well, 5 times 3 equals 15. So that's pretty close. So how would I get it to 14? Then I would just subtract 1. And that's another way to generate it. Looking at this, now we have to put it all together in our function notation rule. So we're going to write f of x for our output. Now will equal, so we said that the m is going to be whatever we multiply. So we multiply by 3, so we write the 3. Then we have the x. And then we have the b. So the b is whatever we add or subtract. So we subtracted 1. So I'm going to write -1. And that's it. I'm only going to give you guys 2 today because it is a new and complex thought process. So I want to go a little easy and we'll get harder as we go through the week. That's it. Enjoy. You guys are doing great and I look forward to grading your work.